All right, so we'll do one more problem, the type of problem where you have to set up a proportion to eliminate one of your unknowns or one of your variables. And this one deals with a trough. So it says a trough is 12 feet long and 3 feet across the top. Its ends are isosceles triangles with altitudes of 3 feet. Okay, so again, in a lot of these problems, you can't even get started until you have some sort of picture in your head. So let's draw out what this is. Let's visualize it. We have a trough, which is basically like like something that holds water that you feed animals in. Okay, its ends are isosceles triangles. Okay, so let's say you have this trough, right? Isosceles triangles. That means these triangles, there's leg lengths are the same, and you have something that looks like this. Okay. And again, just picture this like this filling up with water. It's animals feed out of it. And let's just start to label things. 12 feet long and 3 feet across the top. So we also have an altitude right here. That's the height of that triangle. Okay. So let's call that altitude h for height. That's the height of the water inside of it, and that's going to be 3. Okay. Let's call let's see, 3 feet across the top. So this width right there is going to be 3. Okay, these are all in feet. Its ends are isosceles triangles. All right, we mark those with tick marks. And it's 12 feet long. So let's call this the depth of the trough. You could call it the width, either way, is 12 feet. Okay, so 3 feet across the top, 3 feet deep, and 12 feet long, or 12 feet deep. Okay, now let's read the problem here. It says water is being pumped into the trough at 2 cubic feet per minute. All right, that tells me that that's a change in volume. Okay, cubic feet per minute, change in volume with respect to time. How fast is the water level rising when the depth is 1 foot? Okay, so now it's saying you've got some water in here. Okay, maybe we can use a different color just to picture it. You've got some water in here, and that water is 1 foot deep. Okay, let's set up our volume equation. So volume, now this is a triangular prism. Okay, so we're going to do 1/2 times the base times the height. That gives you the area of the triangle, but then you have to multiply it by the depth, which is going to be 12 feet. So that all together would give you the volume of this triangular prism, this trough. Okay. Now it's telling us how fast is the water level rising when h is 1 foot. Okay, so we have, let's look at what we have. Our h is, it's telling us, is 1 foot, so we got that. Let's take a look at this other variable, d. Okay, the depth, well, let's look at this picture. The depth, okay, which is essentially the width of the trough, is never going to change. No matter how much water is in there, it's always going to be 12 feet across, right? So we know that's always going to be 12. Okay, the part that we're missing right now is this base, because yeah, we know the base is 3 feet across the top, but what about right here, right? This base, that's what it's asking us about. This base at that instant when that height is 1 foot. Okay, well, now that's a variable that we need to think about eliminating, or somehow setting up a proportion to eliminate it in the equation. So we can set up a proportion. Let's look at those triangles again. Okay, we have 3 feet across and we have 3 feet deep. Okay, well, no matter what your height is, okay, now this was 1. Okay, we're looking for our new, so this was our height, this was our base. So if I say 3 was my original base, okay, I'm going to put that over my new base and set it equal to 3 was my original height, and I'm going to set it over my new height. Again, I know my new height is 1, but I just want to write b in terms of h. Okay, original base width, new base width. Original height, new height. Okay, so now let's write B in terms of H. So I'm going to cross multiply again. Okay, so I have 3B equals 3H. And when I divide out, right, you just get B is always going to be equal to H. Okay, that makes sense. If you're starting with 3 feet at the base, 3 feet at the height, well then, no matter how deep it is, your base should always equal your height. Okay, so now if I substitute that back into the equation, I have volume equals 1/2. Now instead of B, I'm going to write H times H. Our depth, we said, is 12. That never changes, all right? That's the width of the water, or the depth back here, or the amount of how wide it is. That's 12. It's always going to be 12. Okay, so if I were to simplify that, I get volume equals 1/2 H squared times 12. Simplified even a little bit more, 12 divided by 2 is 6, so 6H squared. Okay, now we've got ourselves down to a single variable on the left side of the equation and a single variable on the right side of the equation, the right and left side of the equation. Okay, so let's write down what we know we have. We know we have dV dt, and that's equal to 2 cubic feet per minute. We know we have, it's asking us at the instant where the H is 1 foot. Okay, how fast is the water level rising? Okay, that's asking us how quickly is that height changing, dH dt. Okay, that's what we're looking for. So let me just box this off. These are our knowns and unknowns. Okay, so let's take the derivative, both sides. So this is going to be dV dt on the left side is equal to, now I'm going to use the power rule, so that's going to be 12h dH dt. And we have everything we need. We're just solving for dH dt. Okay, so this is going to be 2 equals 12 times 1 dH dt. And when you divide out, you get, just leave this as a fraction, simplified, 1 foot per second equals dH dt when you divide both sides to get dH dt by itself. Okay? All right. Now the second question says the water is rising at a rate of 3/8 inch per minute. Okay, so we've got different units here. These are inches. When h is equal to 2 inches. So let's go back to that volume equation and let's just write our knowns and unknowns. Okay. Actually, let's rewrite the volume equation first. We said it was 1/2 h squared times your depth. Okay. And that's just coming from this original equation. All right, I'm substituting back in the h right here. So let's see what we have. We have h is equal to 2. The water is rising. All right, so this isn't volume. This is actually the rate at which it's rising, the height, as a function of time. So we have, or with respect to time, so 3/8 inch. So again, these are all in inches. And this is going to be inch per minute. Okay, determine the rate at which the water is being pumped into the trough. So that's what we're looking for. We're looking for the rate of change of that volume. Okay. The only thing that you really have to be careful of on this one is we know our h. Okay, that's 2 inches. We know our dH dt. These are all in inches. So we're going to have to change the width of our trough, or our d, into inches. Okay, so my d, I know it starts out as 12 feet, but that's actually 144 inches. Okay, so I'm going to rewrite this as v equals 1/2 h squared times 144. And just one more time, v equals 72h squared. Okay, And again, we're looking for dv dt. So I'm going to take the derivative of both sides. dv dt is equal to 2 times 72 is 144, h dh dt. Okay. Let's see, our dv dt, we're looking for that, and so I'm just going to plug in 144. Our h was what, 2 inches? And our dh dt is 3/8 inch per minute. I'm just going to change that to a decimal. That's 0.375 inch per minute, and that's going to give us dv dt. Now when I multiply all those together, dv dt is going to be 108 inches cubed per minute.